This video will be all about intermolecular forces. Intermolecular forces are different than intramolecular forces. Inter is going to mean between. So this is about the forces holding molecules together in a larger sense, compared to intra, which is going to talk about the bonding that's holding one molecule or one piece of something together. Really, for our four types that we're looking at, these three are kind of both intra and inter at the same time. There's a lot of overlap. It's essentially these molecular compounds, when we're looking at covalent compounds, that we're going to further rank them and really see a big difference and wide range in their ability to have attractive forces between other like molecules. Going along with that, then, we're going to look at the first and strongest of the four, which is covalent network. Now, covalent network is, as it sounds, a network of covalent bonds. So while it is an intermolecular force, it's essentially just a repeating pattern of covalent bonds in an intramolecular fashion. Main examples that I will cover will be diamond, silicon dioxide, which is commonly called silica or sand, and graphite. Diamonds and graphite are both carbon compounds, and silicon dioxide is obviously silicon and oxygen. And network covalence can be involving, as you see, only one element or more than one element. Carbon and silicon are typically the main ones that are involved in this, due to the fact that they have the ability to make bonds on every side. This allows this network to kind of expand because it can make bonds repeating in patterns. If you want to see a little bit more information on this, you can scan that QR code. It'll take you to another video. I'm just going to go through a little bit of this right now. So we see diamonds here, and this is our carbon, and you can kind of see that key carbon tetrahedral shape here. So if I look at this carbon, I see that tetrahedral shape, but it is tetrahedral to a bunch of other carbons, and so it's just going to keep that pattern going. And so that is that network that we speak of. Graphite, which is also carbon, is slightly differently set up. So we see carbon here kind of in a ring, still making its bonds in every direction, but it's going to be flat. It's going to be in sheets, which is why we use carbon in the form of graphite in pencils, because those sheets, the forces between the sheets are not very strong. It's just the layers themselves that are covalently network bonded. And then the last example here is silicon dioxide. Much like a diamond, it is going to be very three-dimensional in how it's making its bond. And that is part of why diamonds and silica are very, very strong intermolecular forces and have very, very high melting points. Going along with their properties, we see they're very hard due to the strong covalent bonds. We know diamonds are the hardest substance we know of. High melting points, hard to melt sand or diamond. Don't conduct electricity due to those secured electrons in those covalent bonds, and they don't dissolve in water. We know diamonds and sand, we put them in water, they're not going to dissolve like salt would. The next strongest type of intermolecular forces is going to be metallic bonding. And this is the idea of these kind of positive ions surrounded by the sea of electrons. We can have one metal be involved in metallic bonding, like copper, or we can have more than one metal, like brass, which is copper and zinc, involved in metallic bonding. If you want more info on that, you can scan that QR code for that video. But this metallic sea of electrons is going to influence its properties. So if we look at their properties, we see that metals are going to conduct electricity very easily. and that is because those free moving electrons can have the electricity, which is electrons, run through them. Mainly, the properties we're going to talk about is that they are malleable. If I want to hit them with a hammer, they will get thinner. They will not break in half. They're ductile. I can pull them to a certain point without them shattering, so we can use them for wires. They're good conductors of heat and electricity, and they generally have a high melting and boiling point. This is all due to that sea of electrons. Because the atoms are able to move past each other, because they're not locked into place like other bonds that we've seen, this allows them to not immediately break when pressure is applied, which is their cause for being their malleable and ductile nature. Next, we have ionic bonds. So ionic bonds are solids composed of ionic particles. Again, if you want to watch a video more about them, you can scan the QR code. Now, ionic bonds, if we're looking at intramolecular forces, we're looking at, for example, sodium and chlorine, the fact that sodium is going to give one electron to the chlorine so that way it can have its octet, and that leads to the charges. However, we're not ever really talking about two atoms when we're talking about ionic bonding. We're talking about these crystal lattices, where we're going to have these repeated patterns of these positive and negative ions. When we talk about crystals, ionic crystals, this is what we're thinking about. This repeating positive-negative pattern of ions that are attracting each other. And that's the intermolecular part of it. Intra is just one exchanging an electron with another. Inter is repeating patterns of all these ions being attracted to each other to create this crystal structure. This crystal structure then, if we look at its properties when we're looking at a sample, would be a solid at room temperature, meaning that it is going to be very strongly held. Most can dissolve in water. The polar nature of water helps the ions break free of that crystal structure. They do have high melting points, not quite as high as metals or covalent networks, but still much higher than the molecular compounds we look at. They have low vapor pressure, so they don't really evaporate, and they break along flat surfaces. And the reason for that is if I have this kind of repeating pattern here, where I have positive and negative, if I apply a little bit of pressure here, then I'm going to be forcing those positives kind of on top of each other. And we know that like structures are going to want to repel. And so that causes stress in the crystal, and that is going to cause breakage where those things are forced near each other that don't want to be by each other, and they break apart. They do not conduct electricity in their solid form because those electrons are kind of locked into place in their ions. But once you melt them or dissolve them in water, that gives them more availability to have electrons move freely between the different ions. And so then they can conduct electricity in their melted state or in their dissolved state. The last thing we're going to talk about is molecular compounds. And as I mentioned in the beginning of the video, this is most of what we talk about for intermolecular forces. These are based on polar or non-polar molecules, and there's going to be a wide variety of properties that we're going to see here because of the nature of the strength of those interactions. While we do have a lot of molecular compounds that are solids at room temperature, we find that most of our liquids or gases are molecular compounds, and those are obviously at room temperature. Smaller molecules tend to be gases at room temperature, especially if they're nonpolar. The larger the molecule becomes, the more likely it is to be able to be a solid at the room temperature because those intermolecular forces will increase. Most have very low melting points, much lower than ionic, metallic, or covalent network. That melting point, if they're a liquid or a gas, has obviously already passed. So that alone, the fact that they're not all solids, indicates that they have a lower melting point. Most feel soft in their solid state. And we are going to find that they're made of nonmetals. We usually consider these kind of to be more organic compounds consisting of these elements. They do not conduct electricity in their liquid state, usually, and some can dissolve in water, others cannot. That is based on the polarity of the molecule. So quick summary of properties of those things if you want to pause the video for now to go over. Moving on to different types of intermolecular forces. These are only going to be for covalent compounds or molecular compounds. And we're going to find that this indicates boiling and melting point. It kind of tells us the strength of these attractive forces. Three types: hydrogen bonding, dipole-dipole, and London dispersion. Those are ranked in order as well. First of that is going to be our hydrogen bonding. And hydrogen bonding is going to be an example like water or NH3 or HF. So you need a hydrogen bonded to an F, N, or an O because those are going to give us the greatest unequal distributions of electrons. These are the most polar bonds we can have because of that strong difference in electronegativity. Fluorine has an electronegativity of 4, nitrogen 3, oxygen 3.5, and due to their smaller size and sharing with hydrogen, which has a lower electronegativity than that, we find that these are able to attain a very large partial negative, and hydrogen is left with a very large partial positive. And so the attraction between multiple molecules of water is going to create this hydrogen bond. Now, whoever named this really made it much harder for people because this is not a bond, it's an attractive force. And this often gets confused. So again, whoever named it did a disservice to everyone trying to teach it. These are the elements that are involved in that. This is the strongest out of our three that we're looking at, while there are other factors that can come into play. So again, this here is our hydrogen bond between adjacent water molecules, but not a bond attractive force. The second tier is for all other polar molecules, and the same concept applies. So if we have HCl instead of HF, we're still going to find a slightly positive and slightly negative end because those are polar molecules. But the difference here is that this partial negative won't be as strong and this partial positive won't be as strong because the difference in those electronegativities in the sizes of the atoms is not going to create as large of a imbalance in that sharing. And so we still find that we have this permanent dipole where one end is positive, one end is negative due to their sharing, but it's not as strong as hydrogen bonding. We do see interactions though where they will be attracting each other. So here, this would be a dipole interaction. And again, that is the attractive force between this molecule number 1 and this molecule number 2 that is holding them in their liquid state. The last and weakest type, and often the hardest to understand, is London dispersion forces. This is going to be based on nonpolar molecules. Now, everything has London dispersion, but for nonpolar molecules, it is the only thing they have that is holding them together. And this is purely based on attaining random partial charges by movement of electrons. So those partial charges are random and fleeting. Unlike a permanent dipole, when we have a polar molecule, these are temporary. And so it's really just if they can build up enough electrons on one side to be a little negative for a moment, and that creates some attraction to an adjacent molecule. And so nonpolar molecules, or just atoms like helium, if they just happen to have their electrons on the same side, this side for the moment will be a little bit negative. But compared to this partial negative on a permanent polar molecule, this is very, very small. And this is also permanent on this one, where this is temporary. And that's the biggest difference. We see that there's a momentary attraction here, but as we know, helium is a gas at room temperature, and that's because it's not enough to hold it together in liquid form. General flow chart when we're looking at molecular things. So types of interacting molecules, first we need to see if it's polar or nonpolar. If it's nonpolar, all it will have is dispersion. Now again, everything has dispersion, but if it's a polar molecule, it might have something stronger than dispersion. And so if it's a polar molecule, we need to decide, is it a polar molecule that has an H bonded to an F, N, or O? If it does, then it's going to be hydrogen bonding. If it's a polar molecule where this is not true, then it's going to be normal dipole-dipole forces. So dipole-dipole and hydrogen bonding are essentially the same. This is just extreme dipole-dipole. The total number of electrons also will have an effect on this. So as we increase the electrons, we increase the ability for an imbalance. So as we saw in the other picture, helium with only 2 electrons can't really build up as much of a partial charge on one side of the atom as radon can with its many more electrons. So the more electrons a molecule has, the greater its dispersion force can become. So the general rule of thumb is that we look at kind of the mass of it, or you can look at the atomic number of it involved if you would rather. But the more electrons it has available, that means the more ability it has to build up those partial charges, temporary partial charges, and it will be more likely to be a solid or liquid at room temperature as you get larger. Summary of some of these things. And then we'll pause and do a quick check here. Okay, here are the answers for this A through F. AR, which is a nonmetal atom, would be dispersion. That's the only thing it can have since it is not a polar molecule. For B, we had to draw this to figure it out. You may be able to tell if it would be polar or not based on the formula, but it always helps to draw it out, and we can see that it's trigonal pyramid shaped, which is going to mean it's asymmetrical, which means it's a polar molecule. But it is not a polar molecule that has an H bonded to an F, N, or O. So we're going to say that it's just dipole-dipole for its intermolecular forces. C, again, you may be able to tell this is nonpolar based on the formula, but if not, draw it out. And we would see that it is nonpolar, which means it only has dispersion. For the next one, we have H2O. So again, drawing it out, we see H bonded to the O, polar molecule because of the bent shape. And there is an H bonded to an O here, which means it's hydrogen bonding. And then the last one, we know that this is a polar bond. And so that molecule is polar. And it is an H bonded to an F here, which means it would be a polar molecule and hydrogen bonding. And then the last one, again, drawing it out, carbon-hydrogen compounds are always going to be nonpolar, but we would see that it is nonpolar from our drawing, and so that is dispersion only. And if we're looking at these in terms of ranking them, the one that has the stronger IMF is usually going to have the higher boiling point. So between argon and PCl3, we said PCl3 had dipole-dipole forces. So we're going to say that PCl3 is going to have a higher boiling point. Between nitrogen and water, we said that water had hydrogen bonding, whereas nitrogen only had dispersion. So hydrogen bonding is going to have a higher boiling point, which again should make sense because at a room temperature, argon and nitrogen are both in the gaseous state, and we know that water is in at least the liquid state. So at room temperature, nitrogen has already boiled away, where water has not. And then the last one, continuing with this trend, HF is hydrogen bonding, whereas CH4 is dispersion. So we would expect HF to have a higher boiling point. Again, CH4, which is methane, a gas at room temperature, kind of leading evidence to support that claim. So that will be all of the notes on intermolecular forces.